Okay, now let's first review the option models we discussed in the last class. So the first one is the binomial option pricing model. The assumption of this model is you consider that in the future, a stock has two possible values. So let's say maybe 100, maybe 90, and this one is 95. And then based on this very simple assumption, then we could derive this binomial option pricing model. So the basic idea is we want to replicate the options payoffs using a portfolio of bond and stock. So in the end, you will find out by this replication technique, the payoffs are the same. This implies the cost should be the same, which means the cost of this replicating portfolio should be the same as the price of the option. Right? We will basically restrict ourselves into this single period model. And then we derived a formula. So you can see that when we're valuing the price of the call, then the call can be actually decomposed into two parts. The first part is about the share price times delta. That is, how many shares you want to invest in this replication portfolio. And B is the amount of money you want to invest in this bond. And we have the formula, which gives us the value of delta and B. So basically in homework or exam, you just need to understand how to plug in numbers into this formula. Then you will be able to find out the value of call here. Clearly this CD is the call's price, is the call's payoff if the price, CD is the payoff of the call if the stock price decreases, and CU is the payoff of call if the stock price goes up. And then SUSD basically refers to the share price if the share price is up or down. And RF, of course, it's just the risk-free rate. And then we talk about Black-Scholes model. Again, it's about plugging numbers, right? But you can see that this Black-Scholes model is more complicated compared with the binomial model. There are several components here. These two components are pretty easy to understand, right? So this is basically the share price, and this is the present value of the exercise price. The difficult parts are about this ND1 and ND2. And then, given this formula, it's actually easy for you to find out how to calculate D1 and D2. So the only difficulty here is about this guy, right? This N here. Again, N refers to the cumulative distribution function. And as I said, you're not required to know how to exactly calculate this. Basically, I will tell you, right? So let's say if D1 is 0.1, then I will possibly tell you several numbers, right? So I'll give you something like this. You can see that as long as you can correctly calculate D1, then you can use this number, okay? Okay, so today let's continue our discussion on this Black-Scholes model. So here we want to talk about the replicating portfolio. Remember that we basically learned two models, right? Binomial model and Black-Scholes. Binomial model says, well, I can basically replicate the call with stock and bond. And then the Black-Scholes model tells us the price of the call is given by this formula. Now compare these two formulas. What you can see here is They both have S, right? So basically, if you compare these formulas, you can write something like this. S delta plus B equals S times ND1 minus BVK times ND2. So if you compare the left-hand side with the right-hand side, you can see that this guy equal to this guy, right? And this guy equals to this guy. So basically, Black-Scholes model gives us a very quick way to calculate delta and B. Right? You can see that B equals this and delta equals this, right? Okay. So the delta here is called option delta. And you can see that in terms of mathematics, it tells you the change in the option price given a $1 change in the share price, right? For example, let's say if C equals 0.6 S plus B, right? This basically means that if stock price increases by $1, then you can see that the call price will increase by $0.6. So basically, you can see that delta, right, which is this guy here. You can see that delta, right? This guy, delta, again, it tells you the change in the price of the option given a $1 change in the price of the stock. Okay. This is just one way to explain delta, right? We also have learned in the binomial model, delta can be considered as the number of shares in the replicating portfolio. So you can see that this 0.6 also means to replicate this call options payoff, you will hold 0.6 shares in the replicating portfolio. So to summarize, there are two ways to understand delta. First, it tells you the change. That is, if the share price increases by $1, then how many dollars the call option price will change. And second, you can also consider delta as the number of shares you have to hold in your replicating portfolio, right? And then you can also observe an interesting property from the Black-Scholes model. So what you can see here is delta equals ND1, right? This is interesting. And you can see that ND1 is essentially a probability, right? So this guy is a probability. And in our statistics course, we learned probability has to be positive and smaller than 1, right? So this basically tell you that because delta is smaller than 1, then it means that the change in the call price is always less than the change in the share price, right? Because we know that one way to explain delta is it tells us, right, the change in the price of option given a $1 change in the share price. And now because delta is less than 1, it means that the change in the call price is less than the change in the stock price. So it basically says the price or the change in the price of option is actually slower compared with the change in the stock price. Okay. Another way, Okay. Additionally, we can observe that this guy is smaller than 0, right? So if you think about the replicating portfolio, this basically says to replicate the payoff of a call option, you have to invest negative amount of money in the bond. What does this mean? Well, negative amount of money basically means you're borrowing money, right? So this essentially says to replicate the payoff of the call option, you have to pay you have to borrow money to buy stocks. So ultimately, this implies replicating portfolio is a leveraged position, right? Because you're using leverage to buy equity. So this is a leveraged position. And we know one thing, that is leverage will always increase your risk, right? So if call option can be considered as a leveraged position in equity, this implies call is riskier than equity, right? So that's another interesting result. That is, a leveraged position is riskier than the stock, and because the call option is a leveraged position in stock, so call options are riskier compared with the underlying stock, right? By the way, how do you know that leverage will increase your risk, right? So let's see why leverage increases your risk. Okay, let me give you a very simple example, right? So let's say we have a stock, its current price is 100, and tomorrow it could be 110 or 90. So clearly this would be 10%, and this would be minus 10% return. Now let's say you borrow some money, right? So let's say you borrow how much? Let's say you have $100. Oh boy. So let's say you have 100. So if you don't borrow money, you could only buy one share. And now you borrow additional $100. Now you have $200, right? So let's assume the interest rate is 0, right? Just for simplicity. So now you can buy 2 shares. Now let's see what is your return, right? So if the stock price increases from 100 to 110, your return would be your initial investment 100, and your final payoff, that is 2 times 110, right? Because you have 2 shares, and then you have to return this $100 you borrowed and minus 1. So this gives us I think this would be 20%. Is it this 20%? Yes, it's 20%, right? Now, let's say if stock price decreases to $90, and then we will have 2 times 90 minus 100 divided 100 minus 1. So this would be minus 20, right? So what you can see here is when the return was 10%, leverage will double your return. And when the return is minus 10%, leverage, again, will double your loss. And you can see that why you're getting double return and double loss, because you have this 100% leverage, right? Because you have only $100 and you borrow additional $100, right? So basically you can see that using leverage increases your risk, right? And then if call option can be considered as a leveraged position in its underlying stock, then call option has to be riskier compared with the underlying stock. Okay, now let's see this example here. So P&A Systems pays no dividends and has a current stock price of $10 per share, if its returns have a volatility of 40% and the risk-free interest rate is 5%, what portfolio would you hold today to replicate a 1-year at-the-money call option on the stock? Okay, so here we want to use, so basically you can see that we are thinking about replicating, right? So we have to find out delta and B. Okay, that's our purpose here. And then to find out delta, here we will use the Black-Scholes model. All right, so B would be minus PVK and D2. And then we learned to use Black-Scholes model. We need 5 inputs, right? We need current stock price, that's the first input. And then we need volatility, the second input. And then we need RF, risk-free rate, that's the third. And then we also need time, right? That is 1 year. And then we also need exercise price. And you can see that this is the at-the-money call. We learned in the last chapter, if exercise price equals the stock price, then this option is at the money. So this basically means the exercise price equals stock price, which is $10. So now we have all 5 inputs, so we could finally do the calculation, right? Okay, so let's first calculate D1. So this is logarithm S divided by PVK. I guess it's something like this. I could be wrong, but let me check the formula here. Oh, I'm actually correct. Okay, good. What you can see here is we have T, right? T equals 1. And we have sigma. Sigma equals 40%. And we have stock price, which is 10. And we have risk-free rate, which is 5%. Right? So you can basically directly plug in these numbers, except you have to find out PVK. Well, PVK is easy, right? Because K equals 10, and we have this risk-free rate, and it is just 1 year. So PVK would be 10 divided by 1 plus 5%, which should be 9.52. What happened? 9.524. And now you could plug in numbers. So I will skip this step, just use the answer from the lecture note. Now it's 0.322. Right? And then D2 is basically, what's the formula for D2? Yeah, D1 minus sigma T, which would be 0.322 minus 40% times 1. So it's a negative number. Right? And then we could use ND1, right? So one way to calculate, right? To calculate this ND1 is to use Excel. So let me show you how to use Excel to make this work. So the function you want to use would be norm.dist, right? This guy here. And then let me see, how can I make this work? So why do I get a keyboard small like this? Oh boy, this is a disaster. Okay, so equals normal distribution. And now what kind of x do we want to use here? It's point, so D1 is 0.322, right? So it's 0.322. And we're looking at a standard normal distribution. So the mean here has to be 1, and standard deviation has to be 1. And we're looking at cumulative distribution. So the value should be true. That is, we're looking for cumulative distribution. Okay. So you can see that it's 0.63. It's about 0.63. Let's see if it's right. Oh. So it's 0.626, right? So that's how you could use Excel to find out this number. But again, this is not required. I mean, I will not require you to use Excel to find out this normal distribution. And then you can see that it's also very easy for you to find out ND2. Okay, I will not use Excel. Maybe I'll just copy from the lecture note. So it's minus 0.078. And then you can see that after getting ND1 and ND2, basically delta equals ND1. So delta gotta be this number. And then B equals minus PVK, which is 9.524 times ND1. So this gotta be, oh, sorry, this ND, so where's ND2 here? Oh, we don't have this ND2. So I'll just write ND2 equals this number. Well, clearly I have made a mistake because you cannot get a negative as a probability. So times this. So this would give you, oh boy. Sorry guys, I don't know why I'm getting this lecture note. Okay, great. So this would give us minus minus 4.47. Okay, so it basically means that you will borrow, right, $4.47 to buy 0.626 shares. Okay, next let's talk about the third valuation model. We basically talk about two models to value call options, right? We talk about the binomial model, and then we talk about the very famous Black-Scholes model, and now we talk about the risk-neutral probability model. So the motivation works like this. So if you notice that in the previous two models, we did not know the probability of each future stock price, right? Because remember that in the binomial model, right? When we talk about this, we said we have a stock. Today's price, it is 50. And tomorrow's price, it is 60 or 40. And we never talked about what are the possibilities. What is the possibility for 60? And what is the possibility for 40, right? And then when we talk about the Black-Scholes model, again, if you look at the 5 inputs for the Black-Scholes model, there is no probability. So this basically means without possibilities, we can actually calculate the call options value. Now let's think about this. What happens if we do have possibilities, right? So let's say if we know that the possibility of each possible future prices, it's possible we can use this discounted cash flow model, right? Think about this. As I said, in the binomial model, we have a stock, its prices look like this. But let's say now I say with a probability of 70, the stock price would be 60, and with a probability of 30, the stock price would be 40. And then if we have a call, right? Let's say if we have a 1-year call. Let's say we have a 1-year call. And its strike price is 50. Then you would know that with possibility 70%, the cost payoff has to be $10. And with possibility of 30%, the payoff of the call has to be 0, right? And then what you can see here is essentially the expected value of this call is 70% times 10, which is $7, right? So the price of the call can be discounted by a certain discount factor. Now, the question is here, or the difficulty is here. It's actually not hard to calculate this expected value, but it's quite hard to calculate the cost of capital for the call option, right? So that's the difficulty here. So that's why we did not use the discounted cash flow model to calculate the price of the call, right? But we can actually find out an alternative way to use this discounted cash flow model to calculate the price of the call. So here, if you look at this, here we know probabilities, right? We have these probabilities. But it's hard for us to find out the cost of capital. Think about this. What if it's easy for us to find out the cost of capital for the call option, but instead we need to adjust our probabilities? That is, we can actually find out this guy, but we have to modify these guys. This is the basic idea of using risk-neutral probabilities to price a option's value. So now let's see how this works. First, we want to assume all investors, they are actually risk-neutral. This assumption basically says investors, they don't care about risk. They don't need compensation for bearing risk, which implies that if all investors are risk neutral, then the cost of capital for every asset has to be the risk-free rate, which means if investors were risk neutral, we could discount the expected value of the call option using risk-free rate. So this will make our life quite easy, right? Because we just talked about this. The difficulty is it's hard for us to find out the cost of capital for the call. But in a risk-neutral world, we can just use the risk-free rate as the cost of capital for options. So this makes our life easier. But you can see that in reality, right? Investors, they're not risk neutral. They're actually risk averse, which means if we want to use the risk-free rate as the discount rate, we will have to adjust probabilities, right? In this case, we call these adjusted probabilities as risk neutral probabilities. This might sound confusing here, but you will see this example, which will give you exact steps how to use risk neutral probabilities to price a call option. And I think it's actually the simplest one among three models we have learned. That is, risk neutral is actually simpler compared with binomial model and Black-Scholes model. Okay, so again, let's think about the example we just mentioned. There is a stock. Its today's price is 50, and tomorrow it could have a price of 60 or 40. And now let's assume its risk neutral probability is P. So with probability 1 minus P, its price would be $40. And our task, or our only task here, or our only major task here, is to find out this risk neutral probability. So how can we find out this? Well, it's actually pretty simple, because now we're in a risk neutral world. So we could discount this stock's future values by risk-free rate. That is, the expected value of this stock would be 60 times P plus 40 times 1 minus P. And then we would discount it at the risk-free rate. So let's see, what is the risk-free rate? Oh, it's 6%. Then this would be equal to 50. Right? So now you can see the idea here, right? We're discounting this risky asset using risk-free rate. So we have to use risk-neutral probabilities, right? So it's like when you're having risk-neutral probabilities in the numerator and you have risk-free rate in the denominator, then you will in the end get a correct discounted value. And then you can see that we can basically solve P here, right? So you can see that the numerator would be 20P plus 40. And then this would be equal to 50 times 1.06. So P would be equal to 50 times 1.06 minus 40 divided by 20. You can just punch these numbers on your calculator. Then you will get a P, which is 0.65. So this is basically the first and the most important step of using risk-neutral probabilities to price your call option. You can see that this basically says that in a risk-neutral world with a probability of 65%, the stock will increase from $50 to $60. And next, we can use the risk-neutral probabilities to value this option, right? What you can see here is this option has a exercise price of 50. So it means the option's price would be either 10 or 0, right? Because if the stock price is 40 and the option's exercise price is 50, then the option holder will not exercise this option, right? Okay. Now let me write down these probabilities. So 65% and 35%. And now, using these 4 data points, we can basically price the value of call option. So what it will do is you will calculate the expected payoff of the call option, right? It's 0.65 times 10. Then you will discount it at 6%. So this gives us 6.13. And you can verify that this will give you the same answer with the binomial model. So let's see what is binomial model's answer. Right? You can see that it will give you exactly the same answer. Again, let me summarize. Right? So basically, it's a two-step process. The first step, you will use stock price to find out risk-neutral probabilities. And the second step, you will use risk-neutral probabilities to calculate the expected payoff of this call option. And then you will discount this call option using risk-free rate. This will give you the correct value of the call. Okay. Okay, so maybe let me summarize, right? So first, this P, it is not the actual probability. The stock price will increase from 50 to 60. It is just risk-neutral probability. So risk-neutral probability is the probability which is consistent with the current price of securities, assuming all investors are risk-neutral. Okay, now we can actually generalize this process. So let's say we have a stock, its price is SU or SD tomorrow. And for option, its payoff would be CU and CD. And now we can find out this risk-neutral probability, right? What we will do is we will use P times SU plus 1 minus P times SD divided by 1 plus RF equals today's share price, which is S. So this will solve P, right? So P would essentially be S1 minus RF. So let me see, I guess minus SD divided by SU minus SD, right? So you will get this formula here. And then after getting this formula, you can see that the value of this call would be this P times CU plus 1 minus P times CD divided by 1 plus RF, right? Again, two-step process. First, solve the risk-neutral probabilities. Second, using the risk-neutral probabilities to find out the expected payoff of the call, and then discount this expected payoff using risk-free rate. Okay, now let's see this example here. It's slightly difficult, but still you can solve it. So let's see what kind of numbers do we have here. So let's assume the current price of this firm is $50 per share. So basically you can see that S today is 50. In each of the next 2 years, the stock price will either increase by 20 or decrease by 10. Sorry, will increase by 20% or decrease by 10%. The 3% 1 year risk-free rate will remain constant. Right? So this gives us the RF. Use risk-neutral probabilities to calculate the price of a 2-year European call option with the strike price of 60. This one is slightly complicated because we have 2 years. So first you have to think how the share price will change over 2 years. And the problem tells you that it either increases by 20% or decrease by 10% in each of these 2 years. So this basically means if you draw out the timeline here, right? So today it is 50. And then, okay, I have to draw it here. So, and then on day one, at the end of the first year, you will have 2 cases. That is, increases by 20%, then it will become 60. Or decreases by 10%, then I believe it's 45. Yeah, I think it's 45. Okay. Now, we have to continue to repeat this step. So if, right, in the second year, it continues to increase by 20%, it would be 72. And if it continues to decrease, then the price would be 40.5. And however, in the second year, if it decreases from $60, and by 10%, it would be 54, right? And you can verify that on this path, it's just 20%, right? So let me write down these possibilities. So this is 20%, this is minus 10%, 20%, and minus 10%, and 20%, and minus 10%. And now you want to think the 2-step process. The first step is about the risk-neutral probabilities. Okay, so let's see how this works. So let's first use these 3 numbers. So the risk-neutral probability here, let's assume it is P, right? Then it's basically 60 P plus 45 1 minus P divided by 40. Divided by 1 plus 3% equals to 50%. Equals to 50. Right? So this will solve P. So I will just copy the answer here. So it is it's 0.433. It's 0.433. Okay, so you can see that instead of actual probabilities, now I could use risk-neutral probabilities. So let me write down these risk-neutral probabilities. So the probability here is 0.433. Then this has to be 0.567, right? And then you can verify that. If you use these 3 numbers, you will get the same answer. So you will again have 0.433 and 0.567, 0.433, 0.567. Okay. Now we have finished our first step. So we could finally think about how to price this call option, right? Okay, so think about this. The call has the exercise price of $60, which means if stock price is 72, then the payoff to this call would be 12. If stock price is 54, then the payoff would be 0. And again, it's 0 if the stock price is 40.5. So now we have to think about possibilities, right? So for this 12, the risk neutral probability is, right? How do you get this? Well, because you can see that to get to this $12, we're looking at this path. That is, first stock price increases from 50 to 60, and then 60 to 72. So the probability for this path is 0.433 times 0.433. And then you can see that, okay, maybe first let me find out what's the value for this. Okay, we don't have a value in this lecture note. Okay, maybe let me use my calculator. So it's 187,489. And then you can see that for the value of 0, for the 0 payoff calls, the probability is given by 1 minus this, right? So it's about, I guess, 8, 1, 2, 5, 1, 1, right? And now you can value this call. You will use these probabilities times its payoff divided by 1 plus 3%, which would be how much? 2.12, right? Okay, let me summarize this. This is a little bit complicated because we have 2 years, and then we will still use this two-step process. So we'll first find out this P here, this risk neutral probabilities. However, because we have 2 years, you cannot directly use this risk neutral probability. You can see that for the payoff of $12, we will think about the path, right? So basically you will have to use 0.433 times 0.433, so which gives you this number. And then after finding out the risk neutral probability, this number, you can calculate the expected payoff of this call. Then you could discount it by the risk-free rate because we have 2 years. So you have to use a squared here. Okay. Okay. There's a different way of calculating the payoff rate, the price of this call, but it's not recommended. It's actually more complicated. Another way, which is more conventional, is you will do this. Okay, maybe let me first remove these additional numbers. So another way it works like this. You will just start from the last period and you will go backward. That is, you will first look at this, right? So by looking at this, you will get a call price here. Let's call this call as CU. And then you can you will look at these 4 numbers, and these 3 numbers, and then you will get a call at the end of the first year. So let's call this as CD. And then you can use this number You use these numbers. And you will finally find out this C here. But for this specific problem, you don't need to do this because it's actually more complicated. You can just use this one-step process, right? You don't really need to go back like from the second year and then back to the 1 year and then find out the price of the call. Okay, now let's talk about the risk and no, it's not the return of a call. So let's talk about the risk of a option. We talk about this because in the future corporate finance applications, this piece of knowledge will be useful. So to think about the risk of the option, we think about its systematic risk. So we will use beta to measure the systematic risk of the option. That is, we want to understand how to compute option beta, right? And how do you think about this? Well, it's actually pretty easy. Think about this, right? We have said a call option can be considered as a replicating portfolio of a stock and bond. That is, well, let's say this is a call option. And we know that it's essentially a portfolio of stock and bond, right? And we know how to calculate portfolio's beta. Since our call option is a portfolio, then it's easy for us to calculate its beta, right? So here you can see that beta of this option should be the portfolio weight of stock times stock's beta, and portfolio weight of bond times the beta of bond. Now, how do we find out the portfolio weight of the stock? Well, we know that call equals this, right? So S times delta is the value of your investment in the stock, and B is the value of your investment in the bond. So you can see that portfolio weight for the stock is given by S delta divided by S delta plus B times B stock. And then the portfolio weight of the bond is B divided by S delta plus B times beta of B. But what is beta of B? We know that we're talking about risk-free bond here. So you can see that beta B is 0. That's why you can just remove this part. And now you will have a simpler life, right? So it's just S delta divided by S delta plus B times beta of stock, right? So this is exactly what you're getting in this lecture note. Okay, now let's look at this example. Calculate the betas of the Jetblue call and put options in example 15.3, assuming Jetblue's stock has a beta of 0.85. So let's first write down the formula. So beta of call equals S delta plus B times beta E, that is beta of equity, which is S delta plus B times 0.85. And now all we need are just three numbers: stock price, delta, and B. So let's go back to, okay, I'll just, you know what, let me go back to 15.3. So where is this? Oh, sorry. Okay, now you can see that from the answer here, we can actually find out the stock price is this 5.03, right? And then what is B here? B is given by this guy, right? So B is this number. What is delta? Delta is given by ND1. So this is delta, right? So now we have S, delta, and B. Now just plug in these numbers into the formula. We can find out the beta of the call option is given by this number, right? 3.57. And it's also interesting to see how large the options beta is, right? The stock's beta is only 0.85, but the beta of this option is 3.57. It's pretty large, and you can see that this is a very natural result because we know that call option is a leveraged position in your equity. This implies that the systematic risk of the call option has to be larger compared with equity. Okay, now we could finally talk about corporate finance applications. So first, let's talk about the beta of the risky debt, and then we can talk about agency costs of debt. So the first application is about calculating beta of risky debt. Remember the motivation for this, right? We learned in the previous chapter that if you want to calculate the cost of debt, you have two ways, right? So the first method is to use CAPM. And the second method is adjust from yield to maturity, right? So in that case, we know that the cost of debt equals yield minus P times L. P is the probability of default, L is the loss rate, Y is the debt yield. And in terms of CAPM, we know that R equals RF plus beta times ERM minus RF. But the caveat for debt is when you're using CAPM, you will not use the debt beta. The beta is actually beta of debt with same ratings, right? So for example, if you're trying to calculate the cost of debt for Apple, right? You will not use the beta for Apple's debt. You would first look at Apple's debt rating. If the rating says Apple's debt has an AA rating, then you will look for the beta for AA rated debt, and then you will use that. Then we use that beta as Apple debt beta. So here, you can actually directly use the option theory to directly calculate a firm's debt beta, right? Okay, so let's see how this works. First, we learned in the last lecture that equity can be considered as a call option on the firm's asset, right? So it basically means equity can be written as A times delta plus B. So this is firm's asset. This is really the idea of replicating portfolio. So we know that if you have a call, then you can read this call as a replicating portfolio of stock plus debt. And call is written on stock, or the underlying asset for a call option is stock. So that's why you should use S here when you're talking about call. But for equity, if you consider equity as a call option, firms firm's asset or this call option is written on firm's asset. That's why you should use firm's asset when you're thinking about firm's equity, right? And then we also learned, which is simple, the value of the firm can be decomposed into the value of equity and the value of debt, right? Then combining these two results, let's see what we can do here. Okay. First, let's think about how beta of equity and how beta of equity and unlevered beta, they're related. And then we will show how beta of debt is related to beta of unlevered equity. In this case, you can see that we can basically find out beta of debt from beta of equity, right? Because you could go beta of equity to unlevered beta. And then you would go from unlevered beta to the debt beta. Okay, we have a bounty formula here. Let's see how can we get these formulas. So, first, we learned that the firm's asset can be considered as a First, we learned that the firm's equity can be considered as a call option written on the firm's asset. So basically, the value of the firm's equity can be considered as a value of a replicating portfolio of the firm's asset and a risk-free bond. That is, we can replicate E with the firm's asset and a risk-free bond, right? So again, we will use the same methodology we just discussed. So this is firm's equity. It's a portfolio of firm's asset and a bond. So this tells us beta of equity will be the portfolio weight of asset times beta of asset plus the portfolio weight of bond times the beta of bond. And then again, when you're replicating a call option, you're using risk-free bond. So here you will just remove this part because beta B is just 0, right? And then what is the portfolio weight of asset? Well, portfolio weight of asset is, so this is the value of asset, and this is the value of bond. So you can see that the portfolio weight of asset here is A times delta divided by A delta plus B, right, times BA. Of course, asset beta is the same as unlevered beta. So we could basically use beta U here, right? And further, we know that firm's asset can be decomposed into equity and debt. So this will give us E plus D times delta. And then we know that this A delta plus B is just E, right? So it's just equity. So we could write equity here times beta U. And of course, this will be equal to 1 plus D divided by E times beta U. So this is how you get this first formula. Now let's see the second formula. Well, the second formula is actually easy because according to the first formula, beta E equals delta times 1 plus D divided by E times beta U. So unlevered beta would be beta divided by delta 1 plus D E, right? obviously you can see that according to this formula, if you tell me beta u, I can tell you beta e. And if you tell me beta e, I can tell you beta u, right? Okay, now let's think about det beta. How do you get the beta of det? It's actually slightly complicated. Okay, first we learned unlevered beta equals d divided by the value of asset times beta d plus e divided by a times beta e, right? You're getting this because the market value of firm's asset can be considered as a portfolio of debt plus equity. And then this will tell us beta d equals a divided by d beta u minus e divided by d beta e, right? And we just learned beta u equals this guy, right? So this is ad beta u minus ed. Let's substitute beta u here. It's beta e. We should actually substitute this guy here. So it's basically e plus d divided by e and times delta beta u. And you can see that these e's will just cancel out. So this leaves us ad beta u minus ad delta beta u. So this will give us 1 minus delta ad times beta u. And then again, we know that a can be separated into d plus e. So this will give us d plus e divided by d beta u. So this would be 1 plus delta. So this will be 1 plus delta, 1 plus e divided by d beta u, right? So now you get the third formula. And what you can see here is, if you tell me beta u, I can tell you beta d, right? Okay, and another interesting result about this formula on beta d is, you can see that if you're having a risk-free debt, right? Let's say if beta d is 0, well, because you're having a risk-free debt. In this case, you can see that delta has to be 1. And if beta d is larger than 0, then you can see that delta has to be smaller than 1. So that is, if you have risk-free debt, then delta is 1. We have not talked about this, but if you have a call option which is deep in the money, then delta is 1. When you're having a beta d which is larger than 0, that is, if there is risk in your debt, then delta is actually smaller than 1. And you will see that if delta is smaller than 1, this will have interesting result on agency costs. To be more specific, if delta is smaller than 1, then there will be debt overhang problem. Okay, so I guess that's for, let me see if I can finish this problem. Nope. So let's stop here today.